For some reasons, yesterday's session that was held live did not get recorded very well. Hence, this is being recorded on the very second day, that is 7th of April 2026. Let's begin. I hope you have already gone through the introduction class, a link to which was shared with you all. You may as well follow Pravina Research on YouTube. This is where we post some tutorials and we post our updates of upcoming courses and things like that. So stay connected with us. We would also love it if you connect with us on our LinkedIn. This is where we post most of our Python automations, or if there are any tutorials that we wish to share. So these are all updated there. You may also follow us over LinkedIn or to our Pravina Research profile and stay updated with us with our upcoming courses. Okay, so I would also want you to know that remote sensing and GIS is a theory foundation. This particular course that you have enrolled for is a theory foundation, which means that we will be discussing remote sensing and GIS along with its integration together for various applications through PowerPoint presentations, through some videos, animations, and mm, audio visuals, right? So we are not really dwelling into hands-on GIS within this particular course. It is meant for you to get connected to remote sensing GIS. If you are just starting with it, if you wish to get a very strong foundation in remote sensing and GIS to be able to very effectively utilize it for solving the kind of environmental problems that you are working on for your thesis requirements, for your other research requirements, or just because you wish to gain some skills, gain some foundation within this particular discipline. So certificate in remote sensing and GIS, that is geographic information system, is a theory foundation. We are going to deal with various concepts, techniques, and applications in a theoretical sense. Mm, However, some of us are also concerned about what is the practical module that is coming to this course. The practical module to this course will contain all the aspects that we cover within theory, but in a practical manner. We will be going through the hands-on, so that is where we will be developing our software skills, our data interpretation skills, data procurement skills that comes before all this, and finally to analyze our data and extract insightful findings from the data that we end up processing, that is the results of it, right? So expect a detailed schedule and a timeline uh, to be um, sent your way by 20th of April. Uh, the curriculum is getting designed in favor of this theory course itself. However, enrollment to this practical module will be optional, which means if you wish to enroll, you may go ahead and enroll for it, right? So for this theory course, coming back, we are starting from 6th of April 2026. The duration planned is 2 months or 4 weeks. We are meeting every Monday, Tuesday with a gap in between, that is on Wednesday, and then Thursday and Friday. So weekly 4 days we are meeting: Monday, Tuesday, Thursday, Friday, in the evening 8 to 9 p.m. So sometimes you expect the class to be finished a little early, which will be good, but then expect some days wherein we extend maybe 5 minutes or 10 minutes, isn't it? So that we cover up whatever the topics that were planned on that particular day. The class is being held online, which means it will be held live. You can attend to it from your convenient spot, mm, at home, after your work, after your college hours. So there won't be a problem in that sense. If you happen to miss the live class, that is also fine. You may go through the recorded session. So if at all something goes wrong with the recording, like it happened yesterday during the live session, it will be re-recorded on the second day and shared with you, so that we ensure that there is no halt in your progress, right? So if anybody still wishes to register for this, because this first session is going to be open, you might have received it from your friends or colleagues or from your teachers, and you wish to register for the live session, that means you will be able to attend the live sessions. Register for it before 10th of April. After that, it will open only for self-paced. That means there won't be a live support. There won't be any interaction that we will be able to have with you. All right, you may reach out to us on this number. Pravinya.co.in is our website. Please visit there and look for the previous courses that we have held, and they are also open for self-paced mode. Let's get going. So I said you can expect the practical module details to be sent your way by 20th of April. In this particular course, the Theory Foundation course, we have 9 units, um, and all of them move in this direction. You understand remote sensing, the concepts around the remote sensing, then geographic information system, then the integration of it, and hence then forward the applications and what are the recent trends that are showing up in this discipline of remote sensing and GIS. So we have in detail covered the unit in our introductory session, that a link to which was shared with you. However, let's just go through these different units that we are going to discuss within this particular theory class. So unit 1 is fundamentals of remote sensing. Unit 2 is sensors and platforms. Unit 3 is image interpretation and analysis. So this is where the data processing comes into picture, and then digital image processing. Moving forward, we understand the fundamentals of GIS. So this unit 5th onwards, we are starting with GIS, spatial data handling and analysis within a GIS project. And then once we learn what is remotely sensed data and what is geographic information system, we go for integrating these two. After integrating in unit 7, we go towards unit 8, where we apply these integration of remote sensing and GIS into different disciplines like agriculture, forestry, urban planning, water resources, climate studies, biodiversity and wildlife monitoring. And then on, in the very last unit, we look at the emerging trends, or what is the future direction of this discipline, in which direction the humankind is leading with respect to processing remotely sensed data in a GIS environment and on different platforms. So now there comes into picture even online platforms that can fetch your data online itself, process it, and give you the results, and the results you can directly go for uh, representing in your reports and things like that. So these are the things that we will look into, also along with artificial intelligence, machine learning, that includes also deep learning, and the very recent mm, advancement, something that everybody is looking into, is unmanned aerial vehicles, that is drones and high resolution mapping. So moving ahead, let's start with our first unit from this 8 minute onwards. Fundamentals of remote sensing is the first unit. We have planned it to be for 4 hours. If we finish before that, well and good. But if we extend it, please understand that we have the first unit, which is the foundation of remote sensing. Here we are going to look into the definition of remote sensing, how to define. If somebody asks us what exactly is remote sensing, then we will be able to tell them in the most best and most sorted way as to what exactly remote sensing is, how remote sensing has evolved through time, different aspects of it, how different aspects of remote sensing has evolved through time, and what is the history of remote sensing from where we began and until where we have reached. If you scan this QR code, you will be able to reach our WhatsApp. Um, this is a GIS community WhatsApp group that you will be able to uh, join. And if you scan this, you will reach our LinkedIn. You may also follow our Pravina research profile there. So even if you have not scanned it before in the live class, you may do it now, or the links as well, to which we will be sharing with you. uh, we also have a have an Instagram handler, and if you wish to follow us there, definitely go ahead. We usually put some maps that we make, and our upcoming courses and things like that over there. All right, coming to the definition of remote sensing. Anytime that we learn any new discipline, it is always suggested that we go through what exactly is the definition, how to define a certain discipline. So when we say remote sensing, let's break it uh, into two words, that is remote and sensing. So when I say remote, what comes to your head is a remote controller, isn't it? You're using that device to control your television, your fan, your AC. You're not really going to your AC and pressing onto buttons to change the mode or to change the temperature settings and things like that. You're remotely operating it with the help of a device that is using infrared sensors. We will also talk about what exactly this infrared is. And then sensing. Humans have five senses. We can see, we can smell, we feel the touch because we have skin. It lets us know, yeah, that yes, somebody is touching us. And then we can hear sounds. Then we can also taste different mm, things, like we can taste mm, raw mangoes, we can taste something sweet, we can understand what taste it has. So five sensory organs we have. Now, here, when we say remote sensing, you have to understand that it is not just one discipline. It's an amalgamation of different disciplines together, which includes computer science, physics, it includes chemistry, it includes earth sciences. So, all these disciplines come together, atmospheric sciences, meteorology, everything comes together to play its crucial role and acquire information remotely. That means without coming in direct contact with that object, may it be clouds, may it be water bodies, may it be forest, may it be urban land. So without coming in direct contact with all these planetary features, objects, we try to sense information from it with the help of all these disciplines together. So here a certain amount of creativity as well comes into picture. Hence, remote sensing becomes not only a science, but it is also an art of acquiring information about that object, about that area, or it may also be a phenomena that is occurring on the land, in the atmosphere, in the ocean, without visiting it physically, without coming in direct contact with it, right? So what we do in order to acquire this information, we use sensors to detect how much of light is getting reflected or getting emitted, how much of energy is getting reflected back or getting emitted from these objects, from these planetary features, from these planetary phenomena, and then analyze that information for its spatial pattern, how it is distributed spatially, or how it changes with time, how it changes with different locations. So all this information we sense without coming in direct contact with it. So anybody, if they ask you what is remote sensing, what you're going to say, you're going to say that it is a science and art of acquiring information without coming in direct contact with any object. Here, these objects are planetary features, um, they are planetary phenomena, and we acquire this information then to um, address different problems that we are moving about now, that we are investigating. Now, coming to the second topic, which is history of remote sensing. Often students have asked me why to even be bothered about history of remote sensing, and I would say it helps us get connected to our roots. Now, why exactly this? Because I should say, when remote sensing was initially put together, it came into light, it was simple. So understanding it at its root is very, very simple. And as we move through time until recent, we realize how sophisticated, more precise, and more yielding it has become. So, understanding something now which has already become sophisticated might become very difficult. You won't be able to connect the dots. But when you start from the very beginning as to how it started, what made it be pursued, and what made somebody execute it, everything is settled. Your interest is also made more consolidated when you look at its history from where it began, right? So the history of remote sensing can be divided into five phases, wherein the early observations were are dating back before 1900. So here people are more concerned about how my village that I live in looks from far, right? So what is the landscape of my province, what is the landscape of my village? I would really want to know how fields, residential areas, then manufacturing areas, the water bodies are disposed with respect to one another. That is one very intrinsic query, I should say, that every human being will have about its own surrounding. And that is why you will often go climb some mountains, trek to a hill mountain, and try to have a bigger picture of the area, right? Even when now we have drones and we have um, different things to not really use our legs to walk up the hill, but still we do it because it also gives a sense of belongingness, that I know my area very well. So these people before 1900 would climb the nearest hill, nearest mountain, to have a wider perspective of the area that they live in. And then comes this person, Gaspard Felix Tornachon. What he does is that he takes an aerial photograph with the help of a balloon. He ties a camera to this balloon and takes a picture. Uh, you know, mm, Sorry, not a balloon. Not a camera. He uses a hot air balloon to go up and take a picture of his neighborhood. And from there we start with something called aerial photography. So aerial photography is the history of remote sensing. That this is from where we realize that having a wider perspective from vertically upward, having a bird's eye view of our area gives us better understanding of how we can plan our areas, right? Then onwards comes people who are trying to take photographs with the help of balloons, with the help of kites, with the help of pigeons, and they are trying to observe and study their areas. This is before 1900, early observations. And then comes this device, stereoscope, that got devised in during the world wars, that is during this 1900 to 1945. So here we are talking about both World War One and World War Two. This is where people were more concerned about their resource. They don't wanted their resource to be destroyed by the rival countries, and at the same time they were also looking for harming other rival countries, machineries that was used in the war. So locating it was very important even before destroying it. And how do we locate it? By definitely understanding how far it is, what is its configuration, what kind of area it is left in, or which areas are safe for us to store our resources and things like that. So here aerial photography era has started, wherein we are making use of aircrafts for making or you know mm, for mapping the different terrains within our country as well as within the other countries. Now this we are talking about with respect to one country. So if I am fighting the war with another country, I would want to know their terrain as well as I would want to know my terrain. And here comes into picture surveillance. So aerial photography was used for surveillance, for reconnaissance, to understand the first hand information about other terrains. And because these photographs were two dimensional, there was a problem. People were not understanding which is the high locations, high elevated regions, which are the valleys and things like that. So here comes into picture stereoscopy. So what stereoscopy does is that it takes two pictures of the same terrain, okay, one from a different location, another from a different location, much like how we have right eye and left eye, and then these two images are placed under this stereoscope. It has this lens. We look at these two images with our uh, with one of our eye, that is the right side image will be seen by the right eye, left side image will be seen by the left eye. So it gives us a 3D, a three dimensional perspective of that terrain, right? So we get to know which are the valleys, which are the mountains, and that makes us understand our terrains, and also plan where to store our resource and where exactly somebody else's this was the basic idea when the aerial photography era started. So that is the second phase. Then comes the third phase. Now countries are uh, speculating third world war as well. The first world war has happened, second world war has happened. Who says that third world war won't be there? And I want to be prepared for the third world war. I would want to know um, the terrain of the entire planet. No matter which country, I would want to study every country. I would want to study my country in much more detail, plan my safe places beforehand, and plan for winning, basically. So NASA has launched its the very first satellite, that is Tyros 1. It stands for Television Infrared Observation Satellite Program. So this the first satellite that was launched on April 1st, 1960, was launched by NASA, and this is post World War, right? After the World War, where people are um, investing a lot into research and development, so that they are planning to win the next wars. So here we are developing two types of photographies: infrared photography and radar photography. So what exactly is infrared photography? Have a look at this particular picture where you see several cars and some humans who are walking over the street. Here what you see is that here you might be able to see the sky, isn't it? It's a window to the sky, and it is darkest object here. Okay. Then you look at these buildings that are lighter in color. Look at the tires here of these vehicles. They are brightly lit. Otherwise, if you look at the car, perhaps a tire is going to be the darkest object, but here you will see that they are brightly lit. And then you see humans, the clothes that they are wearing, so those parts of their body which are covered by clothes, they appear darker, and their face, their legs, which are not covered, they appear brightly lit. Now what could be that insight about infrared photography? Infrared rays is something that humans cannot see. What humans see is only the spectrum, the visible spectrum, that is Vibgyor colors, correct? No, so they humans no cannot see infrared, but they can feel infrared. For example, yesterday I was telling you that if your mother has roasted chapatis, and she has removed the pan from um, the stove, and she has kept it aside, she will tell you, Baba, you make sure that you don't touch the pan because it is very hot. Like looking at it from far, you won't know that it is hot, but then when you come closer to it, you can sense that heat. And that exactly what is what is infrared, right? So infrared radiation is has sensitive heat. You can feel heat every time that you move out in hot sun. What brings warmth to you is this infrared. So here you will see those objects which are warm. For example, these tires that are continuously running, frictionating, hence producing heat, radiating heat, they stand out brightly lit. And those areas which are cooler, colder, like the skyline, that is uh, like the sky window, that is the darkest because it is the coldest, right? So with respect, relatively, you can see in between also you have several objects that are falling between this darkest sky and these brightly lit tires. Also similarly, within these humans, you will see their face is brightly lit, their legs are brightly lit, and that is because those are the regions which are warm, okay, or exposed to the sensor. So, infrared photography helps us sense warmer objects and distinguish them from the colder ones. And relatively, we can also see which is the hotter areas or hotter objects, and warmer objects, and then the colder objects. Okay, so that helps us in sensing different things. Humans are always looking for their replacements, at least to some extent. Maybe we might not be able to clone another human and make them do whatever we want, but we would want to uh, you know um, manufacture such robots, or invent such mechanisms which will replace at least some part of it. So here, identifying cars, identifying humans on road is something that a person would not find it very convenient to do it by himself. So they are looking for some sensors that can do it on their behalf. So this is how we are basically inventing different machines, different sensors, and things like that. So that is about infrared photography. I hope you have understood this. This is used to detect different objects based on their temperature level. And then comes the radar photography. What exactly is radar photography? Now, when I'm using radar ray, so what I said is that, sorry for the disturbance. Okay, so in the, over the land, you what you see is as if paper, some salt, some pepper is s- sprinkled. Okay, so again and again you will see that the pixel color changes over here, different shades of gray color. But then when you look at the water body, it is more even, similar color, or rather very less of changes within the color of the pixels you will see. Okay. Now, so which means that using radar photography, we are able to sense the ruggedness that is present in a terrain. For example, if I was to look at Himalayas, I will see often the pixel color changes. Okay, very irregular or heterogeneous colors of neighboring pixels I will see. But then if I'm looking at the water body, which has a planar surface, obviously there are waves, but then we also have to consider the resolution, which is a little poor. So no, we are not able to resolve the undulations within the ocean surface. On a larger front, we are observing it as a planar surface, and hence you will see that the water bodies can be very distinctly separated from that of the land portion. Here also you will see that the river can be very well identified. Okay, those regions which are planar, radar rays will show it as uniform ones, and the ones which are rugged, it will show it as an heterogeneous, uneven one. So, Tyros, as we said, is the first satellite that was launched. It monitored our cloud cover of the planet, and we could see how storms look, what is their pattern, that they have an eye, what are the tracks of these storms. We could see all this. However, this particular satellite, it worked only for 78 days. It produced around 19,000 images during its lifespan of that 78 days, which is roughly 2.5 month only. But it gave us a lot of insights into our weather patterns. Now, I would want you to keep this in mind that these satellites, no, they are not, once they are launched, they are not ever living. Something goes wrong with the machines. So then they form space debris. They are of no use. They are just rotating around in the um, space, unless and until there are some R&D done to bring down this debris and maybe just burn it off in midair while it is coming towards the planet's surface. So this is it about the third post-war phase. Moving into the next one, the fourth phase is where we have launched one revolutionary satellite. It is launched by NASA in the year 1972. uh, they named it Earth Resource Technology Satellite, or ERTS-1, launched on July 23rd, 1972. You know what is the specific interest of this Lancet one? Until now, researchers, students, everybody who is trying to study the environment that they are studying in the past, how it was, we can date back to 1972. We can use satellite Lancet one satellite data because the CRTS one was renamed as Lancet one later. And now you will see Lancet 1, 2, 3, 4, 5, 6, 7, 8, and the recent one that is Lancet 9 that was launched in 2020. So we have this data available of 1972 onwards. There's a continuity, and we are able to observe our region almost every year in different seasons, how it has changed. And all this data is available for free of cost. You don't have to pay anything for this Lancet 1 data. It is available free of cost in the public domain. One importance of this Lancet one was that it had sensors that could perceive colors of the planet like how humans perceive them. Humans see blue, green, red primary colors and in between different combinations of this, and these sensors could do that. Not exactly as that of human eyes, but similar to it. Okay, and what we call them is multispectral sensors, not scanner but sensors. So these could see and sense red color, blue color, and green color. And when we combine them all, different colors also show up. So here in this image, you see this red color that is representative of vegetation, okay, because it also has an infrared sensor on it. We will talk about how infrared and vegetation is important together. So here, dark red colors indicate deeper or healthier vegetation, denser vegetation, and the lighter red colorations or off white yellow kind of things, puff colors, no, those are the regions where scanty vegetation is available. Now also this Lancet one did not require you to take a printout of how we used to do for aerial photographs. Here we could process the image over the computers itself. Okay, digitally we could process the data. If we wish to take up some mathematical operations on it, we could do it. And because it could see similar to that of human eyes, and it could also be transferred digitally, processed digitally, mathematically operated also, hence we started using it for a wide application. We started using it for wide purposes like agriculture. In agriculture, we started using it to study the crop rotation patterns, um, to study our land use, land covers, to study the different types of rocks in places where we could not go, maybe in the deep rocky deserts we could not go there, very hostile region, but we could study different types of rocks that are present there. Then we could study our forests. Earlier we had to take a printout of our region, mark the boundary of forest, then take another one of different year, mark the boundary, overlap it, see where are the changes occurring. But now we are able to do it on our computer systems, desktop systems, and it can also be distributed widely over digital platforms. We are able to apply it into studying our water resources, whether they are shrinking, they are getting polluted, what is the response of policies that we have undertaken to manage our resources and things like that. All this we could do. Now, one more thing that I would want you to know is the concept of data availability. Whenever you are searching for any satellite data, you have to know on which day it was launched and on which day it was decommissioned, unless and until it is still operational. Okay, so if you are trying to search for data set of Lancet 1 before 1972, you won't get it because it was launched on July 23rd 1972, and then it was decommissioned in 1978. It retired in 1978. That means it was no more producing any images. So if you are searching for Lancet 1 dataset after 1978, you are not getting it. So data availability is very important. The satellites get either decommissioned, maybe because there is some sensitivity problems that have come up in the sensor, the batteries have stopped getting charged, or that there is some significant drift in the planned satellite orbit and things like this. So various different technical problems come, because of which either they are decommissioned or that they retire, they stop producing quality images or stop producing images at all. So this is the image that Lancet 1 has taken. This is Lancet 1 picture. Moving on to the modern era, after 2000, we started pushing in a lot more satellites, not just Landsat 1, Landsat 2, Landsat 3, Landsat 4, 5. But then after that, we started pushing in a lot of satellites, which are high resolution satellites. Their resolution was down to level of meter and below that, sub meter level, that is below 1 meter. For example, Google Earth imageries, they have a resolution of 80 centimeter, 80 centimeter by 80 centimeter. That means even a specific roof tile I'm able to locate on a building. Okay, but then if I use satellite data, I'm not able to do it then. So what are these high resolution data set? Econos, QuickBird, Sentinel, Cartosat. Sentinel has a resolution of 10 meter by 10 meter. So 100 square meter of area you are able to see. Unlike that of Landsat 1, Landsat 1 had a resolution of 60 meter by 60 meter, 58 by 58. Just around figure 90, 60 meter by 60 meter. So such a huge area. Within that, if there was any heterogeneity, I was not able to perceive it. I was not able to study it. But now I am able to do it at centimeters level. When I am mapping, I'm able to take a satellite image. I'm able to study my region much better at the at its core heterogeneity. We have also started using this high resolution data, integrate it with the GIS, process it in GPS, process it in GIS, collect some ground data with the help of handheld GPS devices, so that we are able to correct what the satellite is saying if there is any error. We are also using AI for automations. We are automatically redoing our repetitive tasks. And then comes drones. We shifted from ground based to air based, then we shifted to space based, and now we have again done a lot major innovations in our air based remote sensing. That is where we are using drones for very high resolution, ultra high detail resolution mapping of our terrains. So if I have a plot of just 250 square meters, then I would want to study each and every centimeter of it, and I'm able to do it with the help of a drone images rather than using a satellite image. Then we are also moving into real time monitoring. I would not want, let's say, only one image to be available every month or two images available every month. I would want to see every day what are the changes that are occurring in a region. For example, in agriculture, the crop could be yielding, could be ready to be harvested within 3 months, after 3 month, third month. So in that case, I would want to see every day what are the changes that are occurring within my field. And for that, I am using real-time monitoring, maybe with the help of drones, maybe with the help of these geostationary satellites that keep looking at the same place. And hence, I have a lot of data, what we call big data. It requires to be analyzed. Moving into evolution of remote sensing, and I would want you to know that evolution in history is different, in the sense that history we have divided into multiple phases, that is 5 different phases. In case of evolution, we are looking at different aspects of remote sensing that are getting evolved simultaneously. So first one is platform evolution, where earlier we used to climb the hill, look at the data, or mount a camera on a pole and look at the region from a little height, or climb a tower and take a picture and study the region. From that ground base, we shifted to taking pictures using balloons. Then we started taking pictures from helicopters, airplanes, aircrafts, and then we started sending satellites to the space. Okay, so we there was also evolution in the platform. Now we have come back to we have done a lot of innovation in air based platform, and drones also we are using. Then comes the sensors that are also getting evolved. Earlier, we used to use photographic cameras which could sense colors in grayscale, no red sensation, no green sensitivity, blue sensitivity, only grayscales. So we could not use color and tone to distinguish between different objects. But now we started using multispectral data. After that, we started using multispectral data. So um, within, let's say, Vibgyor color, that is 7 bands of colors, you have 3 sensors mounted each at primary color, blue, green, and red. Okay, so that is multispectral. Then let's differentiate it between hyperspectral. So after multispectral, we started using more conjugately spaced sensors. For example, within that space, same Vibgyor color, earlier only three were there, red, green, blue. Now I'm placing sensor at every color, that is violet one sensor, indigo one sensor, blue one sensor, yellow one sensor, orange one, red one. So seven different sensors are mounting at different at each and every color component. So I'm able to sense more information, much better information, to study the chemical, physical, or even biological characteristics of the object. Then we also moved from passive sensors to active sensors. So what exactly passive sensors are? It doesn't have its own source of light, it has to depend on some external source of light like that of sun. So only when sun is shining bright in the sky, it is sending some radiations towards the planet. They are getting reflected by different objects and the sensors are sensing it. This is a passive sensor. If it is night time, this passive sensor will become blind. It won't be able to see anything. But then we started moving on to active sensors like radar and lidar. They have its own emitter. That means it has its own source of light. And that light travels towards the planet, interacts with the planetary objects, and is reflected back towards the sensor where it is sensed. So now the problem the I will should say advantage of active sensors is that whatever kind of light or whatever kind of energy it is emitting and sending towards the planet, it knows its character, what is its frequency wavelength, at what frequency wavelength it has emitted it, what is the intensity and everything it knows. And after this light interacting or this energy interacting with the planet, when it comes back towards the sensor, now sensor is able to see the changes. If there is any frequency change, wavelength change, it is able to sense it. So we have made innovations in our sensors in terms of being from passive to active, and also photographic cameras to multispectral to hyperspectral. So understand this difference between multispectral and hyperspectral. This is an important aspect here. At the same time, the kind of data that we are utilizing is also changing. So earlier we used to take analog signatures, wherein the signal was coming as just a graph. But now we are also having digital signal. So earlier we used to maybe take a printout of this aerial photographs and see what is the boundary of this vegetation, mark it on this image, and after another 10 years another image, and mark it and see the overlap, see the difference that has occurred. But now we don't have to take a printout of it. What we can do, we can over the system itself, over a computer system itself, using a compatible software which is able to display, which is able to mathematically operate onto this digital signals, we are able to analyze our data. Okay. From resolution also, we have shifted from very low resolution that could hardly see any heterogeneity. We are moving into more higher resolution or ultra high resolution data sets. So we are able to see the heterogeneity within environment much more clear. So look at this particular strip. This is 1 kilometer resolution. Each pixel will have 1 kilometer width, 1 kilometer depth, and then here you see 30 meter. Okay. Then from static images, that is, we just had one image of a region, we are moving into time series, wherein after every maybe 2 days, or after every 16th day, we have some images that are available. After every 1 month, we have some images. So time series data it is called. Then we also have real time data. Right now, what is the weather pattern, where exactly cloud cover is present over India, then I am able to see this, right? So that is called real time data, where these geostationary satellites are constantly looking at just one um, portion of the land. Then coming to spectral evolution, while this data is also getting evolved, while the platform is getting evolved, while the sensors are getting evolved, the spectral evolution is also occurring. Earlier, we used to use only visible region, that is with your colors. Then we started also using infrared to sense the temperature changes within our land. Then we started using microwave, radar, all the parts of the electromagnetic spectrum we started using. Though humans were not able to see it, they devised such sensors that could sense all these energies. Okay, now this enabled us to understand the environmental changes. For example, if I want to monitor health of vegetation or density of vegetation or growth stage of vegetation, then I can utilize this infrared data in association with visible spectrum to study the health of the vegetation, what we call normalized difference vegetation index or NDVI. At the same time, I'm also able to identify regions which are more susceptible to, drought. So wherever soil moisture is low, let's say below 3%, then I know that it's been pretty long that it has not received any precipitation, which means it is under famine, likely to come under drought. Then those regions which are now getting saturated, so I know that there is, waterlogging that is happening there. So soil moisture also we started monitoring. We also started identifying mineral deposits wherever high concentrations of a specific economically viable mineral is available. We are able to explore it without visiting that place beforehand. So we are able to bring down the areas that we have to consider for exploration. So it's saving a lot of money for us. Then the applications are also evolving. You must have heard me saying that during World War I and II, we started taking aerial photographs. So for military purpose, we were using this remotely sensed data. Now we started utilizing for the betterment of the civilians as well. We started using it in our agricultural field so that we maximize the yield by maybe identifying those crops where there is any disease outbreak, isolated from the rest of the crop, ensure its yield, and take precautionary measures whatever is required. So we are able to do this. We're also able to see which areas are more susceptible to flood, why, what are the causal factors for this flood, mm, what are the damages that a recent earthquake has left on a given region. So we are able to do this all because of remote sensing. We're also able to plan our cities, where to place waste disposal site, where to place water treatment facilities, how to manage our water resources, land resources, where the residential area has to be, where we have to plan green spaces. So all this we are able to do with the help of remotely sensed data. Then we are also able to identify those regions which are emitting a lot of greenhouse gases, using these remotely sensed data. We can also plan our surface water resources, groundwater resources. We are able to explore for where exactly a lot of groundwater is available, good quality of groundwater is available, unpolluted resources are available. And all this culminates into one thing, that is we are able to monitor our environment. What are the changes that are occurring in our environment? Why they are occurring? All this we are able to do because there is an evolution in application. New methodologies are coming up. People are devising new techniques to process the data, to find answers to these sticking questions where we are trying to uh, move in a direction of sustainable development. So this picture you will see, here there are three bands, basically three sensors that are collecting images. One camera or one sensor is sensing blue. So those areas which are more blue, like water body, will stand out. Okay, will have high reflection in blue. Then those areas which are highly reflective in green, for example vegetation, will show up brightly lit in this band too. And then there's a red sensor. Those areas which are more redder, maybe barren land and things like that, they will show higher reflection as compared to that of any other. So there are three different images that are coming up. We merge them and we see a combination of all these three. Right. So this is the last topic for the day. Let me see you in the evening, where we start with the next topic, which is basic components. We are discussing energy source, atmosphere, target, and sensors in the evening. See you all then. Have a great day ahead.